All right, we're Calculus Unit 4, Day 28 notes. Our objective to differentiate equations that are implicitly defined. We got the beginning part of the notes here, a lot to talk about, and let's jump right in, then we'll kind of retrace what we talk about, and then we'll look at some examples. So, much of algebraic study of math so far has dealt with functions. In pre-calc, you talked about two different types of equations that relate x and y, both explicit and implicit, much more dealing with explicit functions. um, or explicit equations, excuse me. Explicit equations in x and y are such that y is isolated on one side of the equation. We talked about this a little bit with graphing calculators, so many times you're trying to get y equals. And it equals an expression that is totally in terms of x. So y equals, and y is on one side all by itself, and then x and other numbers are on the other side. So when we see that, I can explicitly tell if it represents a function or not. So in other words, when I see y equals square root of 25 minus x squared, I know that for every x, there's only one y, making this equation a function. Okay, and real quick, we're talking both of these are, we remember these hopefully as equation of a circle, x squared plus y squared equals 25, because x squared plus y squared equals r squared. So now this is just the top part of the circle. And now when I see y equals plus or minus the square root of 25 minus x squared, I know that for every x there are two y values, making this equation not a function. So up above, if I just see the top part of the circle, hey, the vertical line test only crosses once, so it is a function. Down here, and I'll draw it right here, obviously it's the plus square root of 25 minus x squared, and negative square root of 25 minus x squared. So when I do the vertical line test, for one input, there's two outputs, therefore it's not a function. Okay? So now, down below, implicit equations are very different. Um, Typically, they do not have y isolated on one side of the equation. Often there's a power on the y term or terms in the equation, and both y's and x's may appear throughout the equation. So from our conics, um, study of conics, the equation x squared plus y squared minus 2x plus 4y plus 16 equals 0 is a circle, and calculus can be applied to implicitly defined equations. So what we're going to do in this lesson, we'll see how to differentiate those equations that are implicitly defined. I'll also have some other videos attached to the Google Classroom as well, just so we can get some more examples of what um, implicit equations look like. All right, so let's look at this bottom example here. So, um, and we're going to start to talk about, and I've brought it up a little bit um, through our study of both Leibniz and Newton. Um, so we're going to utilize alternate notation for the derivative. So instead of f prime of x, we're now going to start using this more dy dx. So again, it's kind of blending the notations. Um, so let's think about how we differentiate y equals square root of 25 minus x squared. That's explicit form. And then we're going to differentiate the implicit form of the same thing, x squared plus y squared equals 25. So let's do that right now. Okay, so just like when we started talking about function notation, we had up to that point always said y equals, and probably in algebra 2, maybe in algebra 1, but a lot of times pre-calc, we started talking about function notation f of x. So y and f of x are the same thing. Well, in derivatives, we said, hey, y prime, but we said we can then call it f prime of x, and we slowly started to introduce, and we're going to use that almost all the time now, um, dy dx. And again, think of what the derivative stands for. It's the slope of the tangent line. Well, what does the slope stand for? Hey, that's change in y over change in x. So this is, we're taking the derivative of function y, and we're taking it with respect to x. So that's another way to look at it. Okay, so first I wrote this in with rational exponents, so it says square root to the 1/2. So now let's take the derivative of this. So we say dy dx. We have to use the chain rule. So it's going to be 1/2 25 minus x squared to the negative 1/2. times the derivative of what's inside. That's negative 2x. All right, so now let's simplify this. dy dx equals 1/2 times 1 all over, and so this part, the 25 minus x squared, is to the negative 1/2 power, so I'm going to put it on the, from the numerator to the denominator, and instead of writing it in as a rational exponent, I'm going to put it under the radical, and it's minus x squared, and then times negative 2x over 1. Okay, I can simplify, I can cancel out these 2's, and so now the derivative of this explicit equation, dy dx, equals negative x all over square root of 25 minus x squared. And let's see what we get when we do this when it's in implicit form. So now in implicit form, it's x squared plus y squared of 25. Now the hard part is we're so used to saying, hey, y prime. Well, now I just start taking the derivative, and it's the derivative with respect to x. So the derivative of x squared is 2x. Now, normally I would say, and I'll write it over here, well, then it's 2x, and then I say dx because I took the derivative of x with respect to x, and hey, that's just equal to 1, so I don't even need to write that. But now here, what's the derivative of y squared? Hey, that's 2y, and then I took the derivative of y with respect to x, so I have to write that dy dx. And then the derivative of a constant is 0. And now, just like over here, I have dy dx equals, now I just have to solve this for dy dx. So first thing I'm going to do is subtract 2x from each side. That's gone. So I have 2y times dy dx equals negative 2x. And now I want to get dy dx by itself, so we divide both sides by 2y. Okay, obviously those are going to cancel out. Over here, the 2's cancel out. So let's see what we have. Dy dx equals negative x over y. And if we think about what our original equation was y equals square root of, let me write it here, y equals the square root of 25 minus x squared. That's what our denominator is over here. And that's really just y, so those are the same exact things. Obviously, we didn't have to rewrite it. If it's given it to us in implicit form, I could just leave it like that and just jump right into the derivative. So it's meant to save us time, all right, but we have to know what we're doing. Okay, that's going to be part 1. As we look at the next page, there's going to be a couple practice problems that we're going to do and to get better at implicit differentiation.